everybody, welcome to another episode of the Stray Basilisk coding stream. This is Jason. I'm starting a little late today, maybe half an hour late, so I'm going to get stuck into things straight away. So today you may have seen, if you checked out our Twitter post or on our Discord, that we are going to try and make something called the Burning Ship Fractal. This is what it looks like. If you're not familiar with what a fractal is, I mean, it's a term I think most people have heard, but what a fractal is essentially is it's something where if you zoom into it, it tends to look the same, right? It's kind of it's similar to itself at different levels of detail or zoom. Probably the most famous fractal is this thing here called the Mandelbrot set. And there's loads of GIFs and videos around of people zooming into this. So you'll notice that as we zoom in, we're starting to see this same like bulb shape appear at different levels, right? Like you zoom in, and then you can kind of keep zooming forever, and the detail is kind of infinite, and then you start seeing like things which look similar but like distorted and repeated. It's actually not the best example. Let's see if I can find like a YouTube thing. Wow, there's like a 17-minute video of this. There's loads of these, and this is like a really common... No thanks. This is a really common project, I think, for people to play around with in terms of like graphics and rendering. Yeah. So the Mandelbrot set has this very distinctive shape where it has these kind of bulbs. But you can kind of already see how it's similar to itself, right? You've got this kind of big ball and then like a smaller ball. But if you look here, there's also another big ball with yet another smaller ball. And again here, there's a big kind of ball with a smaller ball kind of attached to it. And as we zoom in and in, we'll kind of see more of these things appearing, right? And this thing has like infinite depths to it. It's kind of crazy. Yeah, again, more of these little big ball, little ball patterns. Now we're into something totally different. There's this kind of swirling vortexy thing. But this vortex, it just kind of keeps going down and down and down. These are like super hypnotic and amazing things to look at. But what's even more amazing is when you understand how these things actually work. Which is that that's ultimately a very, very simple mathematical equation. In fact, let's get the equation for Mandelbrot. This is it, right? We'll get into this and like what exactly this means, but ultimately this is something really simple, which is somehow producing this crazy, I mean, literally infinite complexity. I mean, look at this thing. There's a 20-minute video of zooming into it, and it's just trippy AF. And it's also just a really fun little graphics project to do. Relatively simple to implement, but there's loads of ways you can kind of optimize this to make it go faster. So this is Mandelbrot set, but everyone does the Mandelbrot set, so I thought I would break the mold slightly and pick another fractal, which is actually, the mathematics is very, very similar, and it's kind of even related mathematically to the Mandelbrot set. Side tangent, like everything seems to be related mathematically to the Mandelbrot set. It's like pi, right? It's one of those things that everything kind of loops back to. But there's something similar called, which is based on very similar principles, but just a slightly tweaked equation, which produces this thing called the Burning Ship. Burning Ship? Yeah, the Burning Ship fractal. And to be honest, I wasn't super aware of this. I was just looking for interesting things to do instead of the Mandelbrot set, and this looked super cool to me. You can kind of see why they called it the Burning Ship. It looks like kind of a ship that's kind of falling into the ground, and there's either fire, or these also kind of look like, you know, like the rigging on a ship, or even like towers in a city or something. You can kind of see how it's similar to itself at different levels, right? Like you have a big tower, but the big tower is kind of made up of smaller towers, and you can sure as hell bet that if you keep zooming in here, there's going to be towers all the way down, and weird spirally things, and all sorts of crazy stuff. This looks kind of crazy chaotic here. Yeah, so let's make this, shall we? I figured for my own amusement mostly, I'm going to use Golang again to do this. So we used Go on one previous coding stream, which is to make a Discord bot. The reason I want to use Go is because it can be fun to think about how to optimize this and like parallelize the code which runs this. And Go is really good for that, so it's kind of a toy project. Also, I've never done anything in Go involving drawing graphics on the screen. It's mostly known for like server code and like command line stuff, but it can do graphic stuff, I am led to believe. Probably the first step is to find a library which will allow us to do that. I don't know off the top of my head what will do that. So normally I'd have done this before the stream, like done a bit of research. I know there are like OpenGL wrappers for Go, which I will maybe search for now. Or even just Golang, simple graphics. All I need to be able to do is like have access to a window and to be able to set the colors of different pixels. So I'll have a quick Google for what's out there in terms of graphics, simple drawing rendering library. Golang Reddit, let's see what people say. Pixel. Let's see what this library does for us. 2D game library in Go. Take a look at features. Do shader stuff, that's interesting. Shall we go for the first one we found? You know, using a full-fledged OpenGL thing could be a bit complicated. Fractal hype. Okay, cool. Great to have you here with us, Miliv, in any case. Fractals are exciting. Like these are fun. And it's kind of magic when this stuff ends up working. Off-screen drawing to canvas. Okay, that's probably what we want. Let's see if we can find like a getting started thing. You know what I first need to do is initialize my project. I even forget how to do that because I'm new to Go. I think it's Go mod init, is that correct? Okay. Aha. There we go. Let's make a folder. Is my text too small? I will. Can I zoom in? Oh. Well, that zoomed the whole UI. That's not exactly what I wanted, but maybe that's a good idea for yours benefit. Okay. Man, I'm so rusty I forget the exact. Okay, cool. You have Hello World working. So the next thing I'll need to do is to pull in this little library we're going to use for rendering. Go has this nice go get command we can use. Boom. Download for me, please. And while it's downloading, I'm going to check for like a, you know, like the Hello World example. Examples. What I really want is something incredibly basic. So honestly, these are probably all more complicated than I need. Okay, you need to import a couple things in here. Interesting. Okay. So it looks like we need to implement this run function with our code, and we just call this to kind of kick everything off. So let's indeed do that. Maybe this will just give us a blank window. Let's nope. Okay. Okay, so we create a window. Okay, there's something weird here. Happening. We need to bail on this library if it doesn't work quickly. Okay, let's bail on this library because I do not like too much messing around. Okay, this looks way nicer. Okay. I say way nicer, I mean way simpler. So I like simple for these streams. Interesting. Save the output to a file, which is not what we want to do. We want to actually display this in a window. This can do that, right? Maybe not. Maybe this can just output to a file, which is not quite what we need. Did I make the wrong choice with Go? Okay, kind of what I want. Okay, this looks like it made what we need. Okay, so it looks like we need to implement the kind of interface here with an update, a draw, and a layout thing which returns the dimensions. Some color stuff. Okay, third attempt. Thinking ebi-10 is Japanese for prawn tempura, shrimp tempura. I think that's where the names come from. Where's that little cheat sheet? You know, all of these like rendering game libraries have a certain amount of like scaffolding, boilerplate code you need to implement. So kind of got no choice but to do that. Make sure we include this. We don't have that same issue with some obscure dependency. Okay, they've changed the API, that's not ideal. Okay, we have a window. Awesome, awesome, awesome. Nicely enough, this will also do some kind of scaling for us. So maybe one thing to think about is what scale should this thing be drawn at? So typically the Mandelbrot set has a preset kind of range here, where it goes, okay, you probably can't see this. So it goes from -2 up to 1, and then -1 up to 1. And I believe the burning ship has a similar range, which will like nicely frame the thing. So I think in terms of our window size, we should make this the same size, which is basically 2 by 3, or 3 by 2 in terms of proportions. So for example, let's find something that fits nicely on screen. So we could have 900 by 600, for example. Let's be ambitious and render at the same resolution. Fractals can be kind of expensive to compute and render. I mean, that's what this whole project's about, but sometimes you might want to like, you know, downscale them and not. This resolution gives us, you know, 500,000-ish pixels, which is, and you have to do a calculation for every pixel. Okay, that seems to fit on screen reasonably well. Awesome. let's start organizing some of this code a little bit. So fractal.go. What does this image do? Can I just set pixels? That would be lovely. Oh yeah, look at that. So 100 by 100, let's set it to, what's this type? Color, okay. So I've never used colors in Golang, I guess that's a built-in thing. Color dot, come on, give me something. I find the support for Go in VS Code is pretty good, but the autocomplete is not as fast as I'd like it to be. Can I do like color.rgb? I can indeed. So, and are these integers or floats? Integers. So, okay. Let's try and run this here. Oh. Oh, okay, it's image color. Oop. Ready? Is this a function? What is this? Oh, it's a struct. Okay. Interesting. Okay. So what I should actually do is not. Oh. I should just initialize a struct like that. And there. If I zoom in for you guys, we should see a little red pixel. Okay, so I'm able to set pixels. Let's try something to see how fast this is, right? Because depending on how this is implemented, this could be like super slow to set every pixel. So let us try something like can I get screen width? Let's see what you have. Bounds, okay. And that's internal, so it must have a... Okay, size. So width and height is equal to size less than width. Let us set x, y to okay, so I forget how RNG works in Golang. Close some of these tabs, sorry. Ran dot, okay. So if I want to set these colors randomly, I can do something just like this. This is going to be horrible, and the Twitch compression is probably going to hate it, but it's a good test to see how fast we can just display some stuff. Where are we? Missing semicolon. Programmer's bane. Okay. Not crypto rand, just a regular rand. Math rand. Okay. Yeah, my knowledge of Go's like standard library is not amazing. So cast these to what it actually wants. Go likes to be very verbose and explicit. I'm okay with that. So hopefully if we got this to work, we should see some kind of random static here looking junk. Okay, that's going there. That's a reasonable frame rate. That's probably as fast as we're realistically going to be able to render the fractal. So as long as I can kind of multi-thread this, so the rendering of the fractal is separate from the splitting or updating of this image on screen, we should get a reasonable frame rate, I believe. Okay. So I think all we want to do here is we've got this struct, let's give it an give it a buffer. I wonder if there's like a... Okay, so what are my thoughts here? I should probably explain what I'm trying to do. So we have our kind of main function, which is able to kind of loop through and set every pixel on the screen, which is fine. But we're going to have some other code which is actually generating our cool fractal image. Our kind of, oh, whoa, that went crazy. Which is generating our cool burning ship fractal. And what I want this to, what I kind of want to happen is for this to be running separately, and then our main code is just going to take the latest version and then kind of copy it over onto the screen, so that as we're like moving and zooming and panning around this, there's some like little workers churning away, trying to farm out always, you know, the latest image. Like let's say we zoom right in on a certain part of it, then the image should change, and then as soon as that's ready and available, the drawing code should just pick up the latest version and plop that onto the actual screen. So I kind of essentially want to decouple this, which is like the display update. Update versus the like the fractal generation. And why do I want to do this? It's because, well, if we look at this program that's running, I don't know if you can super tell here. I feel like this is like maybe like 10 frames per second or something like that. That's kind of what I'm seeing. And that's just how long it takes it purely to like update all of these pixels. If we added into that the time it takes to actually calculate the fractal image, then it could be way longer, right? So we don't want to have to generate the fractal, you know, spend some chunk of time generating the fractal, and then spend some chunk of time like updating the display. That means our frame rate is kind of then determined by both of these together, right? Because every frame we'd have to regenerate the fractal and then like update all the pixels on the screen. What I kind of want to do instead is have these separated out, so the fractals are always generated, and then the display is kind of always updating. so that these things aren't like kind of coupled together, right? So when this frame is drawn, we're going to take the latest. We'd have to generate something first. When this frame is drawn, we're going to take the latest version, and then again the latest version. And then maybe this one isn't quite ready yet, so we take the latest version, but now when we come to draw this frame, we can take this. You see what I mean? So these things are kind of being updated separately, and then our screen update is just always drawing the latest version of the fractal, so we're not like bottlenecked on either of these. They're kind of happening independently, and they're each happening as fast as they're like individually able to go. So what I would like is to have some structure here which contains the latest image, and then this drawing code should just take it and like slam it onto the screen. Oh, let's update. Right, so here's the screen. So what I would kind of like to be able to do is take this image and draw it onto the screen. But I don't know if there's a built-in thing. I could just loop over all the pixels and copy them over one by one, but that's probably going to be the least efficient way to do this. Like if there is a blit, or blitting would be the process of taking one image and like pasting it into another one. And maybe there's like a bulk way to do that is what I'm kind of looking for. Which there may be here, right? So this we can call screen draw image. The draw images can take an image and then some options. Okay, it looks like we can pass in blank options and it will just kind of do stuff by default. This image is going to be the same size as the screen, so let's say if right, so if there's nothing ready for us to draw, then we're just going to bail out. We can't draw anything. Otherwise, I'm going to just draw our buffer image, our latest. Let's not call it buffer, let's call it latest fractal image. We just draw that onto the screen. Hopefully that's the right syntax. Which means I could go through now and do, create that thing. Looking for like a new image. Okay, cool. It's a bit hacky. I'll factor this out shortly. And then Alright, so what I'm doing now is I'm just pre-calculating this once when the program starts. So we're going to get one bunch of static and it's just going to be kind of drawn the screen for us. It will kind of hopefully prove the concept. Oh. Aha. If we couldn't create that image, then I'm just going to bail out. There's nothing else we can do. How do I do this? assuming I can pass a nil filter. Kind of just figuring this out as I go along, to be fair. Never used this framework before. What is a filter? Oh, okay. Slightly funky. I wonder what this can do. Oh, it's a scaling mode. Okay. Cool. So that's drawn once. This is technically being redrawn, but we're not kind of seeing that happen. So let's think about having our fractal generation happen kind of separately, right? And let's just re-implement this like random static and see how our frame rate kind of goes. So I'm going to just create a function here called generate fractal. And I'm going to pass in a game because we're going to need access to this so we can kind of update it, right? So, okay. Just going to do an infinite loop. Go, this is how you do an infinite loop. Kind of weird, but works for us. And then I'm going to... So what I kind of don't want to do is create each time a new image. It's kind of wasteful. I should probably keep some set of them and like reuse them, but for now, let's just have it create a new image each time and trust Go to garbage collect it, and then we will figure things out afterwards. So, you know, unless this thing has like a dispose thing we need to do. Dot dispose. Okay. Not mandatory. GC automatically collects internal resources. Okay. So, quick and dirty, we're probably okay not to do it, even though in reality we should. Well, we should do it, right? We should somehow be able to mark something as like over and done with, and then have some part of the code dispose of it. Let's create some constants for like width and height. I think that's going to be useful for us. Width is going to be equal to 900. And we'll just use them here. Width and height. Now, this buffer is going to be created elsewhere. Let's also do like a scale factor. Be 1 for now, and then when we create the window, we can kind of scale that. So this is like logical size. Okay. Doesn't fit like that. Okay. Get the syntax here. Oh, it's not curly bracket, it's a regular old bracket. Okay, that's how it likes it to be formatted. I'm okay with that. Then here, create a new image every time, which is horrible, but it's fine. And then we're going to populate it first. We already know width and height. They are constants. Then I'm going to update the buffer. And then, finally, when we're done, I'm going to post it as like the latest thing. Another thing I should probably do is something like this. Hopefully this isn't a copy. I'm hoping this is okay. It's a pointer. Okay. Okay. Just take a reference to it. So if it changes under our feet, you know, it may be that it gets overwritten while this stuff is running, but we're going to take a reference to it here. Okay. Best comment ever. Okay. Taking the wrong brand thing by default. Go likes really short identifiers, but I'm a bit of a stickler for longer names. Okay, did we get anywhere here? Not quite, we never actually ran this code. Okay, width, height. Let's do this via a lovely Go routine. So we're going to say I wonder if run game probably won't return, will it? So let's say go generate that fractal. Let's make this a pointer since that's what we already have. It's happening with my little mouse scroll wheel there. Huh? One error, which is all fine and good. Interesting. Go line 20. Okay, did not like that. Why is that? I wonder if it's because something to do with the initialization order. So maybe I can do something a little bit hacky like this. So if the game is not started, then do this kind of in the first frame, so maybe there's some initialization it wants to do first. Who knows? I'm kind of guessing that that's the issue here. Okay, cool. You're seeing this, and it definitely looks at least as fast as before. I feel like we definitely get something where sometimes we see the same image for like 2 frames in a row, but that's okay for me. Okay, so we've now got the basic structure laid out, whereby we have one thread here, which is kind of always looking for the latest fractal image and drawing it to the screen, and we have another thread which is just generating fractal images, or for us right now it's generating like random static, more or less. But we can easily replace that with some cool fractally stuff, and yeah, let's do that. I think I was going to say one thing I kind of want to do is maybe not create this new image every time. It really feels kind of a bit dirty. You know what, we'll see if there's an issue and we can definitely tweak that later. Let's add a to-do, like good programmer. The thing is, we don't know. Normally I'd just do something called double buffering here, where there's one image we're working on and one which is being drawn. But the problem is when we swap, we don't know if the other buffer is still being used to like update the screen. Like, yeah. So we'd actually need to like have some more complicated scheme whereby either we use some sort of locking or flagging things as being like used or unused, and when both the renderer and the both the fractal renderer and the like screen blitter decide something's no longer being used, we can then dispose of it. But we can sort something out there. Okay, let's actually have this generate a fractal, right? So what is the burning ship fractal? And how do you render a fractal in any case? So good old Wikipedia will give us the equation for this. Oh, it actually gives us code, which we could just steal. Let's see if there's just a formula. Okay, this is a kind of nasty looking formula, but it's actually not as complicated as it may seem. So let me explain what the hell is going on with this. Oh, no, that didn't work. Let me print screen this. I can draw some stuff all over it. Okay. Here is our admittedly terrifying formula. What does this mean? So normally the way a fractal, or this kind of fractal works, there are other kinds of fractals. This kind of Mandelbrot style fractal, typically the ones which have this sort of rich like 2D appearance as opposed to just being like made of lines. They work in a way whereby you perform this kind of iteration where we have this region in which the fractal kind of exists, right? Which we talked about before, being normally in the range of like +1, -1, and was it -2 to 1? I think that's it. So we'd have our like 0 point like somewhere like here, right? And this is basically just a grid, like a normal like coordinate grid you can think about. And this is our regular number line, right? So here's like 0, here's 1, 2, 3, 4, -1, -2, -3, -4. But rather than using a regular sort of 1D number that we normally think of, we're using complex numbers, which are basically, if you remember high school algebra, there was like I and all of the stuff involving like square root of -1. It's kind of crazy, but you can basically think of it as the real normal component of a number, which goes across this line, and then the imaginary component, which is kind of just like another axis. So a number, rather than just being like 2, a point here is kind of like a 2-dimensional number. So maybe this is like 2, like along here, and then like 1.5 here. That's basically just a point determined by a coordinate, where this is like the what we call the real part of the number, and this is what we call the imaginary part of the number. What real and imaginary are don't really matter in this context. You can just think of them as like XY coordinates for the most part, in terms of generating a fractal, like in a practical sense anyway. If you want to get deep into the math of what this really means, then you have to, I suppose, know what an imaginary number like really is, but it's basically just a 2D grid where each number or each point has like 2 components to it, like an X and a Y more or less. And the real part, which is what we're seeing in this equation here with this RE, is kind of like the X coordinate. The imaginary part is essentially the Y coordinate. So what is this equation saying? It's this is defining an iteration, which is kind of a weird thing to say, but we have this z0, which is given a preset value. Z0 equals 0. And then we have something which says z of n plus 1, so is something based on z of n. What that means is that z1 is somehow based on z0, but there's like some function, some stuff done to it, and that's what this kind of defines here. So we can kind of actually work through a little example where z0 equals 0. Let me actually use my little tablet here. So z0 equals 0. But remember, we're in this weird kind of 2D thing, which is actually kind of more like 0, 0. Or in a more mathematical notation, it's kind of 0 plus 0i. There's this whole imaginary number thing where this component is like a normal number, and then this is an imaginary number. And another way to write that is it's some multiple of I, which effectively like shifts something from, if you take the number 2 and then multiply it by I, it becomes like 2 on this axis instead. It kind of like shifts it around onto this crazy imaginary secondary axis. So that's z0, so which means z1 is going to be equal to, what we're seeing here is, okay, let me actually write this out, equal to okay, so let's kind of work out what this actually means. Re z0 means the real part of z0, which means the kind of first coordinate of it, if you like, this part here. And then this operator here, like the size of, this means like the size of something, so it basically means if it's a negative number, we just chop off the negative sign and make it positive, right? In this case, the real part of z0 is 0, so we're down to like the size of 0, which is again just kind of 0. And then we have the imaginary part of z0, which is the second number, or this bit here, which again is 0, size of 0 or 0. And then we have I here, which basically means hey, don't forget this is actually 0i, or this number we've got here is like 0, 0. We're back to the same coordinate since we kind of started at 0. And then we square this thing. So we square this whole thing, which I'll kind of explain how that works in a minute, and then we add some constant. And that constant is, I believe, for every coordinate in here, it has a corresponding C, right? So if we're trying to calculate the color of the Mandelbrot set, or whatever set at like this coordinate, then C is -2 + 1. So for every like pixel on the screen, we're going to plug in a different C, right? So let's say in this case it's -2, 1. So Z1 is equal to this thing which we worked out based on the previous number plus some other thing. Actually, this is going to resolve down to 0, so Z1 is just going to be -2, 1, and then we kind of put that whole thing through this whole process again, right? So the next time -2 is what gets plugged in here. So this would be the size of -2, which would just be 2. And then again here, this would become imaginary part of Z1 is 1, so this is the size of 1, which is 1, so then it's 2 plus 1i, or 2, 1 in our little coordinate star representation, squared, and then adding -2, 1 again. So we have a way to get an initial value, and then to update that to Z1, and then Z2, and then Z3, and then Z4, and then Z5. Yeah, so we could just do this iteration, as it's referred to, for every pixel. We could do it forever, right? But what determines how we display that is essentially what happens to this value over time, right? So we can imagine that we plug in an initial value, which is like up here, and then maybe the second time round, it gives us a number that's like here, and then we apply that same formula again, and we end up with a number that's like here, and then one that's like up here, and then one that's up like here. And the way we draw the fractal is basically based on the behavior of this thing, right? So certain numbers will tend to either stay like totally stable where they are, right? Like 0, 0 is just going to stay as 0, 0, because everything's going to cancel down to 0 and it's just not going to move. Other numbers will like tend to like hop around or spiral around in different patterns, and basically numbers which go crazy and like spiral off like way outside our range are considered, not part of the Mandelbrot set, or are given a certain color, and then numbers which stay kind of stable are given another color. Right, hopefully this will make more sense when we actually come to implement it, and now looking at this pseudocode may kind of help here. Well, it's not -2, it's -2.5. Okay. So what do? So we go through each pixel, we convert its kind of screen coordinates to the coordinates like in our like nice framing of the fractal. And then I don't like these variable naming, but we're taking variables out for the kind of first and second part of the coordinate, or the real and imaginary part of the number, if you like. And then we're doing that same little formula. This is kind of calculating this kind of thing given those sort of x and y coordinates we've got. And then what we do is yeah, so we keep doing that while it's close enough to the center, right? This is kind of doing Pythagoras essentially, right? It's saying if this coordinate squared plus this coordinate squared, which is like a Pythagoras hypotenuse thing, is less than 4, which I believe is equivalent to saying, so we've got some coordinate. If this is 0, 0, got some coordinate here, then we're working out like the x, or the real part, plus the y, or the imaginary part. And then we're kind of calculating the length of this line, which is essentially the distance from 0, 0 that we've ended up at. And if it ever goes like outside that certain range, then we consider it to have like escaped, and we kind of stop at that point. And then based on how many goes around it took us to like fly out, then we can color the thing accordingly, like how many iterations it took. And if it stays inside for a certain maximum number of attempts, then we go, okay, it seems to be like stable. It seems to be like staying within that radius which we defined. So we generally like color it black in that case, right? So let's copy this pseudocode and sort of re-implement that in Go here. Kind of ugly for each pixel in the stream. We're already doing that. We've already got X and Y calculated for us here, so we just need to scale these into our range, right? So hey, Untitled 33, thanks very much for the follow. If this doesn't make sense, by the way, or anyone has any questions, like please do let me know. And it is kind of confusing, and I superficially know how this works, but like the super deep math underlying this, like I'm not an expert mathematician, so I'm kind of winging it slightly. Like I've implemented fractals before, but you know, this stuff is kind of crazy and gets into like some interesting number theory stuff, which I'm by no means an expert in. So okay, so we've got this range, right, of -2.5 to 1 and -1 to +1. So we need to convert from our screen coordinates, where this is like 0 and this is width. We need to kind of then map it down onto this range where 0 becomes -2.5 and the pixel on the very right hand side becomes 1, and then similarly for this. So we just need to do a bit of mapping there, if you like. So let's actually create a little function which does that for us. Map to fractal space. So we're creating a little function here which will take an XY coordinate. Super clear. Now I've got minuses and I'm trying to draw these arrows. In future, when we implement like zooming and panning, this is kind of where we can do that, right? We can apply scaling and offsets to kind of shift and move this thing around. But for now, I'm going to say x is going to be x divided by let's add some constants here. Okay, I'm saying min because the top, I'm assuming the top of the screen is like coordinate 0, but we actually want 1 as opposed to -1 to be up there. So, yeah. Basically, I'm flipping this in the y-axis because that's kind of more convenient for us. Okay. I'm being super explicit with this rather than just shoving it all into one equation because I feel like it's gonna work out more nicely for us. So we're gonna figure out how far along the screen it is, like what proportion, and then we're gonna multiply that by our scale x, and then we're gonna add the min. And then we do something similar for y. Scale y, y. And then just return these. What's wrong here? Okay, it's all this chunk, it's getting confused with. Okay, so let's go through and kind of convert this code like piece by piece. Okay, so the real part is going to be equal to, oh, or actually the real, call it real and imaginary, are going to be equal to the kind of mapping. What was our function called? Mapped fractal space. Okay, we have done that. I've renamed those because I think this is horrible naming. I should probably have a constant for okay, don't need that there. So do this in a for loop. So this is very much Pythagoras. So the sum of the two sides is equal to the sum of the square of the two sides is equal to the square of the hypotenuse. So what do we call it? Distance threshold. So this is what we're really doing. So we're kind of, this is the distance from the origin, and we're checking, or the squared distance from the origin, we're checking against the squared distance threshold. Reason being, to find the actual distance from the origin, we would square root this, but square rooting is kind of expensive programming wise, so it's cheaper to compare it to the square of the distance cutoff as opposed to square rooting it and then just comparing it to regular distance cutoff. Basically, it's cheaper to square this than it is to square root this side, if that makes sense. I'm going to move these constants above. This should also be outside of this. Okay. That's weird. Why is it using X and Y? Shouldn't those have been mapped? Okay, it's scaled. Okay. Oh, because this is C, right? Okay. Yeah, it's trying to add on our constant. So what I should probably do is okay, so what they're also doing here is they are effectively like skipping this first iteration, right? So if you noticed, the first iteration, everything's 0, and then our constant gets added in such that the next time round, basically in Z1, the value is just equal to C. So they've kind of skipped this and just said, hey, let's just initialize things to C and effectively like skip this first iteration. Okay, team relief, take it. So that seems to make sense. So what I'm going to do is save these off here and then kind of like copy them here because I will need them. Okay. What's that calculation they're doing here? What this is here is it's basically the expansion of like squaring this thing and then adding this. They've kind of just condensed that back down into a few lines, so I will trust that they've done that correctly and just kind of steal that logic there. Plus okay, so they're using this temporary because you kind of need to update X and Y at the same time, but if you updated X first, then the calculation for Y would be kind of off. So they kind of use this temporary for that purpose. Okay, I think that's what we needed to do. So for now, let's just do a black and white thing. So if it's maximum iterations, then I'm gonna set this to like white. Otherwise, I'm going to set it to black. What you'd normally do is like a color gradient based on the number of iterations, but we can do that next stage. We should at least get the basic shape of our ship here. Boom. Cool. We have some errors. Oh, you must be on the same line and go, right? Oh, I want to play 64. Should we just use 64? It's a constant, right? So it shouldn't matter. Okay. Ooh. We've got something going. Okay. I feel like we're on the correct track because that seems like it probably fits the shape of this in some way. We are probably like upside down or flipped in some axis, but that's okay. Also, number of iterations and stuff will probably affect various things. Awesome. Okay, let's maybe do the color grading. And then we can play around with like some zooming and panning, and then we can maybe optimize this a bit. Okay, let's in color is going to be equal to okay. If it's in, it's going to be let's do in color is like that, then out color. Let's make it blue. Seems fitting for this ocean theme daily. Okay. Can't have struct constants. Okay. Let's also do func map color. Based on the number of iterations, which will return a color RGBA. Okay. So we're going to take the ratio. It's going to be iteration over max iterations, and then I'm just going to kind of take the components and kind of invert these like this. Then I'm just going to construct a color which kind of blends between those two colors according to this sort of proportion. So it's going to be in color dot red times ratio plus out color dot red times inverse ratio. So what will happen here is this will be between 0 and 1 depending on how many iterations, right? If there are no iterations, it's going to be 0 or close to 0. If there are maximum, this is going to end up being 1, and then this is going to be whatever's left over, right? So if this is like 0.6, this will be 0.4, and then we can kind of add these components together with those ratios. 0.6, 0.4 adds up to 1, so we get like a linear blend, if you like, between these two colors. Yes, so high iterations mean it's in, which means, yeah, that looks correct to me. Let's do green and blue in a similar way. And then, screw it, we won't care about alpha, we'll just return 255. So I need to What type does this want? It wants uInt8. So we'll just convert this here. Since we're messing around with floats and integers, I believe this will do what we need. Okay. Go does not like implicit casting of number types, which is kind of annoying, but I also kind of appreciate it. Oh, I've been calling that function. Getting ahead of myself. So I'm just going to say, I'm going to set the color equal to mapping color based on the number of iterations. Okay, we are seeing something. So I think this blobby bit probably does correspond to this. So probably we're upside down, so let's flip this. Thankfully it's fairly easy for us to do like that. And it also seems like it, so I'm looking at a little preview here, it looks like we kind of want to pan up a bit, so let's just play around with this and like offset this whole deal. I mean, I guess there's no reason not to just like squish things a bit. So what if we made this 2? Not sure if that's the wrong way around or not. Yeah, should have gone 1 and then like -2. Looks a little bit closer now. Okay, we're not doing too bad here. I will maybe make it even higher. Seems like there's loads of interesting detail at the top there. Okay, so we are seeing part of this. So I think what we're actually seeing here is so there's a reason we're not seeing all of these details up here, and that's because I believe it's to do with the number of iterations we're using. So if we increase that, you tend to just see more and more detail. So it would be cool if we could press a key or something to tweak that. So what even was that library I'm using, and how the hell do I tell if somebody is pressing a key? Okay, how do I get some input? Ooh, okay, there's a nice is key pressed. Edge browser, you can run this in the browser? Okay. So let's set some parameters in our game, right? So we're going to want started ball, we've got zoom, float 4, everything else seems to be. Right, so let's actually pull these out of our not make that a constant. construct this game, I kind of want to set some of these things. Where do we construct it? Right, so we just kind of set those up there. Yeah, maybe this as well, you know. Separate out these fractal parameters. So distance is equal to 2, I think is what we had. So let's now pre-calculate this here. And now this can be game.max iterations. Okay. Oop, 52. Okay, all looks the same. Now we can do something like if maybe 10 dot is key pressed. Pressed dot key interesting. Let's say up arrow, maybe page up, then e dot. Let's double it when we do that. Let's halve it, do that. Okay. What kind of key is this? Okay, it's AB10 key. Okay. We don't need any of this junk. Dot key. Okay. Okay, so hopefully now if I press page up, oh, that happened crap ton of times. I probably crashed it. Okay. Interesting. How else can we get some input? So it seems that maybe update and draw are decoupled. So even though it's not ideal, I could put this in my draw loop because that kind of locks us to a frame rate. Okay, going up to 4,000. If that looks any different. Let's also have this print out when it's completed a frame. $16,000. How long is that going to take? Probably quite a long time. Let's see. I kind of want to just let this render a frame to see how it looks. Another thing we can play around with is this scaling. Because right now it's kind of a linear scaling, so we could change it to be like based on a square or something, so or a square root, so that it's like a logarithmic scaling or something. I wonder if we check the thing we can see 64 iterations. Okay, so there's loads of detail there. Okay, let's try a way low number then, because it seemed to be okay at like 64. Oh, you know what? Actually, having a lower thing seems to give us some interesting stuff. Yeah, actually having this too high seems to erode some detail, which makes sense. You've got more iterations, more chance for stuff to disappear, so you'd need finer detail in order to see those. Yeah, let me also make this so that it can't go less than 1. Yeah, so if you add more iterations, we get more kind of detail here. There's parts of this we're kind of not really seeing, and I'm wondering how, or kind of why that is. It's actually rather like this is what we're seeing. If I drop that number down, yeah, it's exactly this kind of thing, right? And these same like bloomy shapes up here. So how is it that they're getting these cool towers? Oh! You know what? I think what's happening is the towers are actually down at a lower zoom level. Okay, so we need to be able to pan and zoom this thing. Right, this is not the whole fractal, this is just like probably like this little part, which is why we're not seeing towers at this scale, but we might see them at a different scale. So, okay, very cool. Okay. So the first thing is to add some more parameters in here. So we got zoom, so I need a pan, right? So pan Y, 64. Okay, so we need some pan stuff going on, and then when we do this mapping, we probably need to give it this whole game thing so it can figure out this stuff. So we've added that. We also need to mapdex times game dot zoom plus game dot pan x. Right, so then we need some controls for zooming. I think probably all we need is something here. Plus key num. Add. I guess they're calling it add. Keypad add, is that like the number pad plus? Is that what they're saying there? Okay, if we're doing that, so we're going to do g dot zoom plus equals, I don't know what a good factor is here. Subtract. And g dot zoom is greater than 1. Okay, we have an error. Because now our mapping function needs the game passed in. Okay, so now I should be able to. Okay, it's the other way around. of course, I need to kind of divide by the zoom actually, because if zoom is 2, then actually the range should get smaller. So I can zoom in, and in, and in, and in, and in. Okay, now I need to be able to pan. Okay. Something like key left arrow. Cool. Key left, then G dot pan X. What does equals? This is not going to work quite as well. What I really need is a way to zoom. Okay, there's something you often have to do with zooms, such that if I just increase the zoom and I'm panned, then it will kind of, the panning will be affected as well, if that makes sense. So what I need to do is probably actually do a zoom which like preserves pan, which is a kind of special thing you sometimes have to do. So I probably also want to pan different amounts based on how zoomed I am, if that makes sense. So if I'm zoomed in, then I want to, the shift should be less, because otherwise if I'm zoomed really in and I pan by like 0.1, then it's going to like shoot me off the whole screen. I'm going to pan too far from like my perspective when I'm zoomed in. So yeah, hey, C and Dunford. It's because it's pretty much for fun. Like I've been learning Golang recently. This is also a nice kind of thing to do parallelization for. So some of the concurrency stuff in Go I think would be fun to play around with for making this run a little bit faster. But pretty much just for fun. Like in terms of graphics rendering, it's a weird choice, I would say. But you know, this is just a little toy evening project just for today, so why not? Okay, we have pan ability and zoom ability. You can pan over here, zoom in, hopefully see these cool towers. Awesome. Blue book and making gifs. Yeah, I feel like it's a weird, honestly a weird choice for generative art. Like I normally use processing, which is like a Java-based framework for that, because it's just very, very painless to get like some basic rendering stuff done. But honestly, I had a bit of a search around for like a good library, and this thing I'm using, Ebi10, seems pretty reasonable. All I'm doing is like individually setting pixels though, so in terms of other stuff, I know there are like OpenGL wrappers and things like that. Okay, there are awesome cool towers. Let's zoom in on these bad boys. This is fun, right? This is where the Fractal Generation starts to get really awesome. I may have to tweak this zooming code to, yeah, so yeah, right. So I was wondering for ages why I wasn't seeing the towers, and it's because they're actually in the like main zoomed out image. They're not actually there. It's only when you zoom into like the, I don't know what you call it, like the sub fractals, that you actually start to see those. What I want to do is change the zooming so I don't zoom by a fixed amount. I'm just gonna like double it, something like that. Well, that's going to be a bit more reasonable. Whoa. Maybe doubling is a little bit too much. Kind of crazy. So I'm actually seeing some tearing here. I don't know if you can see this on the screen. And that's because I'm fiddling with the parameters of this while the like rendering thread's going. I should probably like cache the parameters for like pan and zoom and like not do that, but honestly I'm not too bothered. Oh wow. This is kind of crazy. What I might do is double the scale, just so we can see stuff. Where are my constants? Bit bigger on stream. It's super trippy, right? It's just like very much like 70s album cover material right here. So what kind of stuff have you been doing with Go? Like graphical game dev stuff or more like businessy, typical Go stuff? Oh, I've played around with it a bit for some like back-end like REST web service stuff, and I really like it. With number of iterations. Does seem like there's a sweet spot for seeing interesting stuff here. Yeah, I like Go for like web service stuff. I've played around with a little toy projects doing back-end stuff, and it seems pretty nice. I don't know, it's got Google behind it, right? So that's a certain level of adoption. The community for Go seems really good. Like the library, I mean, the standard library is pretty awesome, and tooling support and stuff. Yeah, it is, right? I mean, it's tailored to like certain specific use cases, I guess, but yeah, I would, for the kind of things I generally like to code, I'm definitely inclined to use it over C. So I'm just playing around here with like the number of iterations, and it seems like unless you're in a sweet spot of like 64, a lot of this stuff isn't visible. Yeah, honestly, it's probably a weird choice for like graphical stuff. Something like this, maybe not, because it's more of like a very parallelizable rendering task, although I guess you should probably just use a shader to do this in reality. Yeah, this is very cool. Let's try and zoom back out here. Towers, within towers, within towers, within weird, twisty, sideways towers. Whoa. This is very alien-looking fractal, right? This looks like some structural xenomorph, crazy alien city stuff. I kind of like it for that aspect. And the way, I think they call this the Armada, right? Like there's this, oh, it's got a very landscapey quality here as well. This is fun. Okay, I think the last thing I will try and do quickly is throw some Go routines at this and kind of very roughly like parallelize the thing. See if we can boost the frame rate. Although to be fair, since the number of iterations is so low, it's really not an issue. Like if I double the number of iterations, like we just lose a load of detail, but I think maybe if I applied a non-linear like curve to the color mapping, then that detail may come back. So maybe that's something we can do. Okay, so how am I going to Go routinify this? I'm going to divide the image up. So there's a few ways we could divide the image up, right? The space up. A kind of naive way is to just chop it into sections, like either like that or kind of like that, and then just create Go routines or like assign different threads to different like slices of the image. The problem is there's not a uniform amount of work required to calculate most of these fractals, right? So, you know, this part is low number of iterations, whereas this part is like really high. So it basically requires no work to calculate like this area, but it requires a load more work to calculate these more dense areas. So what we probably want to do is to do something like divide the image up a bit more fine-grained, like maybe into little regions like this, and then just have like a pool of workers, and then like have them just pull regions off of the queue, meaning that we don't assign one Go routine to like this easy part of the image, right, and have it complete early and sit around doing nothing, while the Go routine that's trying to calculate the body of the ship takes ages because it's got more number crunching to do. So we divide the thing up and then just have a set amount of worker threads, and they just do as many of these as they can, and if they spend a bit more time doing these more intensive sections, then that's fine, because we won't have things like sitting idle waiting around so much. So I'm gonna like prematurely make that optimization because I know it's pretty necessary. So I think I want a struct for, I forgot the syntax for declaring a struct there. So type call it a region, and we're going to give it a, what do we need? It needs a just like this, right? Just give it a region like that, and then we can kind of pass a load of those into a queue and kind of move this into a little worker thread thing. So let's move this out to func compute region. Passing in a region. I'm going to go x is r dot min x. X is less than r dot max x. Is that what we called it? And the y. X, y. Some other stuff as well. Probably use xmin versus min-x inconsistently all over the place. I don't care. Okay. Yeah. This out as well. And then, so if I did something like Let's try like a 32 pixel region, because that feels like a nicer round number. So let's try and iterate through these regions, right? So for x min so we're doing another loop now, which kind of splits this whole space into different regions. Kind of decomposes it into a grid, if you like. So now we can create a region. R is a region which goes from xmin max is going to be alright, we want to make sure we don't go like off the side. Hopefully that makes sense. So we're going to kind of iterate through x by region size, and then also y by region size, and then we're going to say, so our iterator, our for loops will basically give us the top left corner of each region, and then we just add the kind of region size onto that. I've probably gotten off by one error, so these things are going to overlap slightly. I will fix that. Yeah, and this is making sure if we're from the last region and there's only like 10 pixels left, but we're trying to do like 32 pixel regions, then we just clamp it so it never gets wider than, never goes off the side, if you like. So this will be 0. -1, right? We'll see if there's missing spaces here. Okay, so that's okay, we also got to cast this to an integer. Does not like that. Does this have like a min int? Okay, it does. Oh, okay, no. Okay, I thought these were functions that are just like the smallest possible integer value, so I need to go back to casting these. Okay, I don't do anything with R, so let's do, just going to compute it right in the loop here, and we will use some Go routines and a little work queue to do this later on. Okay, so this should be functionally the same. I've just like haven't parallelized it yet, but I've kind of done some preliminary work for that. Oh. Ah, let me give it the buffer to write to, which is a pointer to and it's fine for these to all just write to the buffer at the same time because they're writing to separate regions of the image, so they're not assuming it's just like some array underneath and the library isn't doing something weird, which would make that like non-thread safe. We should be okay. Okay, that's probably enough by one. But this does show us that we're kind of decomposing this into grids in a reasonable way. I think I just shouldn't have done that. Cool. So now the code is kind of splitting this up into conceptual regions. I just now need to throw those onto a channel, right? So, okay. Was it Chan? So we should probably have a buffered channel. Yes. It's going to be explicit here. Right, so I can then make this so basically calculating the maximum number of regions in each axis. Passing that into make, so we get a queue or a channel with enough space for all of these regions, and then rather than computing it, I can just say just throw it into the queue. You can simplify this like this. Okay, we load a load of stuff. So and then we could, before we parallelize this, I can say are in range. You just pull them straight out the same queue like this, and then do compute region R with our game and our buffer. Okay. Once again, it's not really parallelized, but it's shoving stuff onto a queue and then pulling it off of a queue, and something has gone wrong. Okay. Oh, probably this never returns, right? Because queue is empty. What happens? So I probably need like the go tool because I forget the exact semantics of these channels. Where are we? If anyone feels like giving me tips, I am more than open to them. Buffer channels. receives block when the buffer is empty, so I need to do like a switchy thing, right? So select. Select, okay. Yep. I believe it should be more like infinite loop and then select. Try and pull something from the region queue. What's the syntax again? Okay, do case, okay. If we manage to pull something from the queue, I don't like the fact that this isn't indented. I feel like case statements should be indented. God damn it. I think Go will break automatically. Yep. And then I can do maybe a default break. Okay, I think this will handle right, break out when there's nothing more in the queue. Nope, still seeing sweet FA. You know what? Easy to just return. So yeah, right, like people don't even use if else if, you just use like switch all the time, even though you'd normally use like an if else if chain in another language. I think what's happening here is that I'm maybe need to do like break outer, something like that. I think that maybe was the bug there. My thought was if I just refactor into a function I can just return, but I feel like I should make sure I understand what's going on. Okay. Yeah, so, okay, that's how I did it. That should do what I need, right? What's going on here? Can I just scope this? Nope. I don't like the fact that it's indented everything subsequent to that label. Makes me feel like I've done something wrong there. Okay, let's like debug this quickly. Something slightly funky is happening. Either when I am putting them onto here, like I've got the capacity wrong, so this is blocking, or I've got the kind of logic wrong here, maybe. Move this window, please. Interesting, maybe the code never. Okay. You got there. Something bad happened here. Okay, max regions is 1. That's Not at all right. Okay. I got my divisions the wrong way around. So I calculated there's only one region, so I've got a queue with buffer size of only one, so these things can't fit in it. That's what I actually need to do, I believe. So do I just run it? Okay, cool. So that logic is still intact. And I can make this internal. What's your opinion on this whole deal? Like, that being kind of public versus this being private? I feel like it falls in line with Go, like, enforcing conventions, like, you know, the whole auto format thing, the fact that I need a comma on the end of that line because it's kind of adheres to convention. So normally I would hate this, that like this implicitly makes it like public versus private, but since it's all about like adhering to conventions, I feel like it's in the spirit of Go. I don't know. Okay. So we're doing our thing. So now we've got something which can pull from our regions. So this is now our code for our workers, right? So this is going to be our Go routine essentially. Okay, what's the idiom for waiting for a set of Go routines to complete? That's what I'm kind of thinking here. I know there is like an idiomatic way to do that, so not all Go routines, hang on. Waiting for multiple Go routines. Wait group, that feels, I feel like there's a way to do this with channels, that's nicer. Yeah, you're right? Like it's like, normally I would, what am I trying to say? Normally I would dislike having such strict rules, but the fact that it just gets automatically applied kind of makes it okay, right? Like it kind of annoys me that, you know, there's this thing with semicolons or like about how these are like aligned, but the fact that it just auto formats whenever you save kind of, and that's generally how you're expected to interact with it, kind of makes me okay with it being so opinionated. I found that in practice it tends to be okay. Wait for, I know there's a normal way to do this with like a channel, or is a wait group just the way to do it? Okay. Okay, wait group. You add to the wait group. Okay. Yeah, exactly that. And it's the whole thing of all Go code should look the same, which is a very pragmatic thing about in practice, I think. Oh, okay, you just wait 100 times. Okay, I'm going to use the wait group. This seems reasonable to me. Where are we? Okay, so let's say sure we can tweak that. So I can just say add workers. Then I should pass in a the weight group, purely as a pointer. Oh, I can just kind of, yeah, use an anonymous function. That seems fine to me. I can just change this to return. Compute readings from queue. Read queue. Okay. Something is not entirely correct. Okay, let's. There is some more debugging here. Okay. Oh. Didn't signal that we're done. Hopefully that's it. Okay, I've got a bit of code in the wrong place. But this is interesting. It's kind of a cool bug. I think the error is that I have done something. It's something, right? Let's see. Let's add a bit more stuff here. So I hope this is not an issue of multi-threading with this like game rendering library we're using. I think if I turn the number of workers down to 1, you get a sense there. It's 2. Wow. Okay, I've got a sneaking suspicion that this is an issue with whatever. So I'm using this like set pixel dealy, and maybe that's not thread safe. Buffer.set. I'm surprised I can maybe see what it's actually doing. Okay, so probably what I need to do. Yeah, right. You'd expect it to either be like half of the image, or I suspect this is doing something a bit fancier than just setting stuff in an array, right? It's doing this replace pixels thing. Rather than just like writing into an array, which I kind of thought this would be. So maybe what I'll do is change this to, yeah, so it said that it would loading pixels at most once, so maybe there's a way to like there's some mip mapping stuff going on. Okay, what I would like is to be able to have like a raw image. Or I may just have to write this junk into an array and then sort of manually like copy the data from it. So if I made this instead like right, like an array of, or a slice of colors, then I can go, instead of just drawing the image, I can say y is 0. I can kind of just use an array as my buffer, and then I'm a bit safer doing this. And I can do screen.set xy to g.latest fractal image. Right, so I've kind of done like a manual implementation of that, if you like. So my image is just a plain old array, which probably means I can now first of all, I can change this to and it's going to be width times height. Buffer is not just going to be this plain old array, and here, and then rather than calling set, I'm just going to do something similar. I do x plus times width x. This is a very common way to map from like an xy coordinate into like a one-dimensional array, where you kind of store one row after another. This kind of works out the index in that based on the xy coordinates. Equals. If it's not this, I'm going to be gutted because it's going to be just something wrong with my threading, and then all of this would have been unnecessary. Ooh. I've got some. Let me put that back to 32. Oh, I don't know, 8. Okay, I'm probably just screwing up my splitting. Where am I writing into that? That should be right. X is 0, Y is 0. This makes sense, right? We're getting like the first pixels of various things, so just trying to figure out visually what might be happening here. Let's just change this quickly to so I'm setting this to something just based on X and Y, so we can figure out what the hell's going on. Yeah, I've probably got some silly error. Exactly, right? So what am I... I've got... this is... Oh, okay, I've got height and... I've got height and width swapped around. Yeah, right, but that's typically what I do, especially like debugging anything like this. I would just... yeah, set it to something predictable so you can hopefully tell what's going on. Okay, so that seems to be that. I'm not sure what's going on with those boundary edges. Put this back. I want to try changing this mapping. to kind of square it so that it's non-linear. I think we might see more detail do this. Oh, by the way, hooray, it's working, apparently. Let me add actually a little flag to this. You know what, I could do something really hacky. Say if dot is key. So I want to kind of play around with these different color scalings. Didn't like that for some reason. Okay, this is super slow. For whatever reason, it's crazily slowing things down. So a little bit hacky here. So I want to be able to toggle between these things. This one annoys me, that I have to put the else on the same line. That's probably the one like forced convention that genuinely kind of annoys me a little bit. Because it feels like it shouldn't matter. It's weird what's slowing me down here. Okay, so we're actually seeing less detail, so I think maybe if I squared this kind of in the other direction, if that makes sense. I'm super just fiddling now. So ratio equals 1 minus ratio times 1 minus... I don't know what we call this, like a sort of inverse squaring? Not sure. So if I up the number of iterations, but then non-linearly scale the color. Okay, we seem to get a little more detail. I don't know if this is actually a productive thing to do. zoom back to our favorite ship. Okay. I think it's about, you know, these almost look like shadows of ships on the water. It's crazy how scenic this whole thing is. Yeah, nice one. I think we're about to wrap up here anyway. Thanks for joining us for the journey. Next one should be around the same time next week. We do a different project each time. Yeah. So I think I've finished this with one final zoom in. You know what? I like the original parameters. There we go. Another interesting section to explore. It really does feel like you're exploring something. When you see this changing here, I'm just tweaking the number of iterations to see if there's a kind of sweet spot that captures the detail and has a nice kind of contrast. Because it kind of looks patchy like this. I mean, obviously you can always keep zooming in, but okay, I think we'll call it there. Since it seems to be working and is apparently running in a multi-threaded fashion, I will say goodbye to everyone. If you want to follow us on Twitter and vote for the next thing, normally on Thursdays we put those polls out. Otherwise, join us our Discord at discord.gg/StrayBasilisk, where you can follow the development of our main project, Steamhound, which is a turn-based tactical steampunk themed game. You know what, these crazy towers are giving me some inspiration for level design stuff there. Anyway, I think we'll call it a day. Thanks so much everyone for joining us, and I'll see you next time.